started.
Okay, so let's go ahead and get started. So far we've developed various techniques for studying perturbative quantum field theory, and we've studied in some great degree of detail the Feynman diagram technique for computing observables such as expectation values or scattering amplitudes, both for for scalar fields as well as for vector fields such as the photon. And today what I want to do is begin the discussion of the quantization of spinor fields. So, for example, if we wish to study the quantum theory of the electron, then we would be interested in quantizing something like a Dirac spinor psi, which I remind you is a 4-component object with 4 spinor indices, which we usually suppress when we can get away with it. And there are various sorts of subtleties that arise in the quantization of spinors, which makes the subject a little bit more confusing than the quantization of scalars or vector fields. And so what I want to do today is spend a little bit of time discussing how one quantizes fermions or spinors using the path integral techniques, especially to emphasize some of the subtleties that arise which are different from the bosonic case. And so in particular, our sort of goal today is to begin to understand how to derive Feynman rules by quantizing spinors, and I'll be using the path integral technique as we did for deriving the Feynman rules for scalar fields. If you look, for example, in your textbook, I believe in chapter 4, there's a derivation of Feynman rules for spinors using a different sort of technique. I know of at least 3 different ways of deriving Feynman rules, either using the Schwinger-Dyson equations, using the sort of canonical quantization techniques that are used in the textbook, or by using path integrals. Today, so in this course, we're really just focusing on the path integral technique because I think it's the most general and the most systematic. But if you want to look at other ways of deriving Feynman diagrams, of course, then you should take a look, for example, at what's in the textbook. Okay. So to begin, what I'd like to do is just remind you a little bit about the Dirac theory. We've taken a break from studying spinors for a few weeks. So I'll remind you of just a few things of the Dirac theory. And then I'll begin to explain to you why it is that this theory is so subtle to quantize. And especially why the path integral technique is particularly confusing when we think about fermions. So remember that the Dirac theory, so the free Dirac theory is described by a Lagrangian, which is quadratic in psi, where psi is a 4-component spinor. Psi bar here is almost but not quite the Hermitian conjugate of psi, because we have to insert a gamma 0 here. And I'm using the compact notation, this Feynman slash notation, where d slash is both a derivative as well as a 4x4 matrix acting on these spinor indices. And it's the contraction of the partial derivative operator d by dx mu with the gamma matrix gamma mu. Okay. And when we quantized the free Dirac theory, we quantized by writing psi as an infinite sum of oscillators, just as we did for the free scalar field. But we expanded in terms of fermionic oscillators rather than bosonic oscillators. So among other things, one of the things that I argued to you, and something that I believe you confirmed on one of the problem sets, is that if one uses the wrong sort of statistics, so for example, if you try and quantize a fermion or a spinor using bosonic statistics instead of fermionic statistics, then you run into all sorts of troubles. You have energies which are unbounded below, as I think you showed on a problem set. You also have violations of Lorentz invariance and all sorts of other terrible things. The upshot of which is the conclusion that whenever you quantize a spinor, in order to have a consistent theory with Lorentz invariance and a well-defined ground state, you need to expand in terms of oscillators, but you need to assume that these oscillators have fermionic statistics rather than bosonic statistics. So here I'm just writing down the expansion of the free direct field in terms of raising and lowering operators. So let me just remind you here that these U's and V here are the analog of the polarization vector that arose for the photon. So just as when you expand the photon in terms of polarization vectors epsilon mu, when you expand the four-component spinor psi in terms of free solutions to the free Dirac equation, you have to specify the polarization of the spinor. So for example, S here is an index that runs from 1 up to 2, where you sum over the various polarization states of a Dirac spinor. And the two solutions, say U1 and UP, describe, for example, an electron which has spin up in the, so spin up in the z direction or spin down in the z direction. If you choose to, so just as you, for the polarization vector of the photon, can use different bases for these polarization vectors, you could, for example, for a photon traveling in the z direction, talk about linear polarizations where they're polarized in the x or the y direction, or you could talk about clockwise or counterclockwise circular polarizations. When we quantized the spinor field, we had to expand in terms of these polarizations, U and V, and there are different choices of basis for these polarizations. And one of the bases that we worked out was one where if you had an electron, for example, traveling in the z direction, you could either have it polarized with spin up in the z direction or spin down in the z direction. Or, of course, you could choose polarizations in the x direction or y direction or something like that. And we worked out, if you remember, hopefully, specific expressions for what these polarizations U and V look like. Is that all more or less familiar? I mean, we did do it in some detail, but it was about a month ago. Okay. Good. So these polarizations, U and V, are four-component spinors, so they're four-component column vectors, if you want to think about them like this, that are just used to describe different solutions of the free Dirac equation in momentum space. And there's a similar expansion for psi bar. So one of the things that we have to remember is that when we quantize the Dirac field, just as when we quantize the complex scalar field, because psi is not a real field, psi is not equal to psi bar, or psi is not equal to psi dagger. So that means that the oscillators, the raising and lowering oscillators here are not Hermitian conjugates of one another. So, and similarly, the polarization spinors U and V are not complex conjugates of one another. You just have to expand in terms of two different sets of spinor polarizations. And so if you wrote down a similar expansion for psi bar, you would have to, well, you would just have to take the bar of this expression, and so you would get U bar S as a function of P times A dagger with a corresponding expression in terms of V bar. Okay. So hopefully you all more or less remember this. And the interpretation of these raising and lowering operators is that the operator A, for example, creates a particle. So for example, this could create an electron. And the operator B creates the corresponding antiparticle. So that's the operator that would create a positron. So the spinor field psi is interpreted either as creating a positron or removing an electron. Both of those operations, of course, increase the charge of your state by 1. Okay. Similarly, the operator A without a dagger removes an electron, and the operator B without a dagger would remove a positron. And the basic observation that we made was that in order to have a consistent theory, we had to assume that these electrons and positrons were fermions. They obeyed fermionic statistics. which was reflected by the fact that rather than obeying fundamental commutation relations, these oscillators obey fundamental anti-commutation relations. So, for example, if P is not equal to P prime, or if S is not equal to S prime, then these raising operators, there's a dagger here, these raising and lowering operators would obey anti-commutation relations rather than commutation relations. And similarly, for the operators that create or remove positrons. And all of the other operators, so for example, the A's and the B's will anti-commute rather than commuting. Okay? This reflects the fermionic statistics of these particles. It says that if you have, say, a 2-electron state and you interchange the location of the electrons, then the wave function would pick up a minus sign. Good. So when we discussed the quantization of the free scalar field, we didn't dwell on this fact that the operators were anti-commuting too much. We just sort of took it as given. But in order to really think about the quantization of this theory in the path integral language, we're going to have to think a little bit more about what it means that the operators out of which we're building the psi fields anti-commute with one another instead of commuting. In particular, what I want you to do is I want you to think about how we would describe one of these spinor fields in a classical limit where we take h bar to 0. So in the classical limit, what does it mean that we have raising and lowering operators that anti-commute rather than commute with one another? Well, remember in the canonical commutations in quantum mechanics, you have the commutator of x and p as I h bar. And so in the classical limit where you take h bar to 0, that just says that the observables x and p commute with one another. That's just the statement that in classical physics, the position and momentum of a particle are things that one can measure simultaneously. They're classically commuting observables. In the present case, when we take h bar to 0, this term here, so this term is like the I h bar that appears in the fundamental commutation relation. So really, we usually use units where h bar is equal to 0. But if we were to restore our h bars, this is something that would be of order h bar. So it would go to 0 in a classical limit. So what this means really is that in the classical limit where h bar goes to 0, the field psi is some sort of anti-commuting variable. But the thing that I want to emphasize is that it's a classical anti-commuting variable. Now, when we talk about operators that anti-commute rather than commute, if you think about quantum mechanics, if you're always thinking about quantum mechanics, then the statement that something anti-commutes is not so surprising. Operators are operators. They're like matrices. They obey some algebra. Some matrices commute with one another. Some matrices anti-commute with one another. It's not such a big deal. But if you think about some sort of classical observables, objects in classical physics, having things anti-commute with one another is very, very strange. Okay? So in particular, I want you to remember exactly what it is a field means in classical field theory. So if we think about, for example, the model that we always like to think of when we think about an intuitive model of a classical field theory, if we have a bunch of balls on springs that describe some scalar field, then the value of the scalar field phi of x is a number. It's a number that measures the displacement from the equilibrium position of one of these balls on a spring. Okay? And so the field phi of x, so a usual scalar field, phi of x, is just an assignment of a number per each point in space-time, x. And if there's one thing that I know about numbers, it's that numbers commute with one another. If you multiply two numbers together, it doesn't matter what order you multiply those numbers. So what we see here is that if you want to think about the field psi as some sort of classical object, then you can't think about it as a number for each point in space-time, or a set of four numbers, because it's a four-component spinor. So psi of x, whatever it is, it's certainly not regarded as some set of numbers per point in space-time, right? You can't think of a classical Dirac field as a set of four numbers per point in space-time. Although that's really how we've been describing them so far in this class. You know, we wrote down the solutions of the free Dirac equation by writing down, well, a bunch of plane waves and a bunch of numbers for each point in space-time. But the point is that if you want something that classically obeys fermionic instead of bosonic statistics, you really can't think about it as a number per point in space-time. Instead, you have to introduce some sort of new mathematical object. Okay? You have to introduce numbers that anti-commute with one another instead of commute with one another. And so there's a name for this sort of mathematical object. We call it a Grassmann number, or an anti-commuting number. Okay? So in particular, psi is what's known as a Grassmann or Grassmannian number, or really I should say it's a set of four Grassmann numbers because it's a four-component object per point in space-time. And this distinction is important because when we talk about the path integral quantization of a Dirac field, when we do a path integral, we have to sum over all possible values of the classical field, right? When you quantize a scalar field, or when you quantize a free particle, for example, you're summing over all possible values of the position of the particle or the values of the scalar field. And so you're not going to get the right answer when you quantize a fermionic field in this way unless you take into account that the actual classical variable that describes a field is not a number per point in space-time, but instead a different sort of mathematical object. Okay. So for at least the first part of this class today, what I'm going to have to do is introduce just a little bit of mathematics to describe a new kind of algebra, a new kind of numbers that anti-commute rather than commute. Has anyone seen Grassmann numbers before, anti-commuting numbers before? It's one of the, it's actually an important and kind of interesting mathematical subject. It tends not to be taught except in classes on quantum field theory because it doesn't appear in many other circumstances. Although if you've studied differential forms, you've secretly studied the algebra of Grassmann numbers. Grassmann numbers sort of secretly appear all over the place in mathematics and physics, although they tend not to be really studied explicitly as such. Okay? So what we really want to do is we want to imagine that previously, when you learned arithmetic, you learned about numbers, okay? But what we really want to do is we want to now decide that there are two different kinds of numbers. So really, in our theory, we're going to introduce two different kinds of numbers. There are the numbers that you learned about when you were 4 years old or 5 years old. Okay, we'll call these C numbers or classical numbers. And these also we could call commuting numbers. They're the usual numbers that have the property that 4 times 5 is 5 times 4. But there's also going to be a new kind of number, which is referred to as a Grassmann number. Which are anti-commuting. And in particular, they have the property that, first of all, any two, so let's say that you have two normal classical numbers, C and S, they will commute with one another. So here C and S are C numbers. A Grassmann number, let's call it theta, will commute with a C number. So here theta is a Grassmann number. But finally, two Grassmann numbers will anti-commute with one another. So theta and eta, two Grassmann numbers, will anti-commute with one another. And just as you can add and multiply regular numbers together, we can add and multiply together both regular and Grassmann numbers, or both C numbers and Grassmann numbers. So first, let's talk about addition. So if you add together two C numbers, then you still get a C number. If you add together two Grassmann numbers, you get a Grassmann number. So I'll just call it a G number, just so I don't have to keep writing down the word Grassmann. Or maybe I'll call that Grassmann, probably better. And finally, you're not allowed to add together a Grassmann number and a C number. So there's only two kinds of numbers, C numbers and Grassmann numbers, and there's nothing in between. But you can multiply these numbers together. So for example, if C is a C number and theta is a Grassmann number, then their product is a Grassmann number. Similarly, okay, I guess I should have said that explicitly, but you probably know that if you multiply two numbers together, you also get a number. So that's a C number. And finally, what happens if you multiply two Grassmann numbers together? Well, does anyone know the answer to that? If you take two anti-commuting objects and you try and, are those going to be anti-commuting or commuting? So if you take, say, three Grassmann numbers, say theta, eta, and psi, and you take the product of theta, eta, is that going to commute with psi or anti-commute with psi? Does anybody know? It's going to commute. Right. So this is going to be a C number. So you can just verify explicitly that if you have a set of anti-commuting objects, say, if you've got a bunch of commuting objects and anti-commuting objects just as operators, then the product of any two anti-commuting guys is something that commutes with everything else. So the product of two Grassmann numbers is a classical number or a commuting number. And in fact, arithmetic and indeed calculus with Grassmann numbers is vastly simpler than arithmetic and calculus with classical numbers. Okay? It took you several years probably to learn calculus with regular numbers. You'll understand everything there is to know about calculus with Grassmann numbers by 5 p.m. So, in particular, since Grassmann numbers anti-commute with one another, that means that, in particular, they anti-commute with themselves. So the anti-commutator of theta with theta is equal to 0. So that implies that the square of any Grassmann number is equal to 0. that's another way of seeing that the product of two Grassmann numbers has to be a commuting number, because 0 is a classical number. It's not a Grassmann number. So this means, in particular, that if you think of a function of a Grassmann number, you can take functions of Grassmann numbers just like you can of regular numbers. Well, you could imagine Taylor expanding that order by order in theta. And because theta squared is equal to 0, every function of a Grassmann number is a linear function. Any questions on this so far? I mean, Grassmann numbers are sort of deceptively simple, right? Like, it's in some ways, Grassmann numbers are incredibly simple, but also incredibly useful as a bookkeeping device for keeping track of fermionic degrees of freedom. Now, when I talk about a function of a Grassmann variable, I need to decide whether that function f is going to be a classical number or a Grassmann number. If f is a Grassmann number, that means that a and b need to be classical numbers. But if f is a Grassmann number, sorry, if f is a classical number, then that means that a and b need to be, sorry, what did I say? If f is going to be a Grassmann number, a and b need to be C numbers. Whereas if, sorry, I take that back. Okay, so if f is going to be a C number, then that means that a is a C number, and b is a Grassmann number. Or if f is a Grassmann number, then that means that a is Grassmann, and b is a C number. In the first case, then, we need to be a little careful about the order of b and theta in this Taylor expansion of f of theta. Okay. So, for example, if f is a C number, so this is the usual case that we might consider, then f of theta is a plus b theta, which is a minus theta b. Now, one of the things I promised you is that calculus of Grassmann numbers would be much simpler than the calculus of regular numbers. In particular, if the only functions you're allowed to have are linear functions, then it's very easy to take their derivatives. So in particular, the derivative with respect to a Grassmann variable of a function of that Grassmann variable is defined by two properties. So the first property is that the derivative with respect to theta of theta is equal to 1. And the second property is that since theta is a Grassmann variable, and d by d theta is something that removes a Grassmann variable, d by d theta has to be viewed as a Grassmann number as well. You can even see that from this equation. 1 is a C number, theta is a Grassmann number, so that means that d by d theta should be viewed as a Grassmann number as well. So, for example, if you take an arbitrary function, a plus b theta of a Grassmann number, and you take its derivative, then that's either equal to b if b is a C number, or it's equal to minus b if b is a Grassmann number. And then the point is that if you think of the classical variable that describes a fermionic field, such as the Dirac spinor psi, psi is not a number per each point in space-time, but it's really a set of 4 Grassmann numbers for each point in space-time. And this is not something that we've really had to confront so far in this discussion, because the Grassmannian nature of the spinor field really only arises when you have to start doing things like, like studying the path integral approach to the quantization of these spinor fields. Previously, when we quantized these spinor fields, we just thought about them really as operators rather than as classical variables. Any questions before I continue? Yes.
So I'm still, okay, so if you have e to the theta,
Mm-hmm.
and you take the Taylor expansion,
So E of theta is 1 plus theta.
right, but,
We'll come to this in just a minute. It's
Right.
actually an important point. Yes.
okay, but e itself would be a c number, right?
Mm-hmm.
And so the 1 is a c number in the Taylor expansion.
Yes.
And then, so what would
Yes.
be the b term?
That's because good. So that's because you really shouldn't talk about functions like e to the theta. You should really talk about e to the b theta, where b is a Grassmann number. And then that's 1 plus b theta.
Right.
We'll come to this in a minute. Yeah. So you really can't talk about something like e to the theta, because that would.
The assignment likes to do that.
What's that?
The assignment looks like it does that.
Oh, did I?
Oh, there's an e to the 1 plus theta.
Hopefully. Oh shoot! I should have put some constants in there. Okay, sorry about that. Yeah. Okay, I take that back. There's some circumstances under which I suppose one might want to add classical numbers and Grassmann numbers. People do often do that, and it looks like I did when I was writing the problem set. What I was doing is I really wanted you to compute Gaussian integrals, but they were a little too complicated. Okay. Maybe let's rephrase that. We're not usually allowed to add classical numbers and Grassmann numbers. It's something that formally makes sense, but it's not something that we usually do. In particular, if you add together a Grassmann number and a classical number, you get something that's neither Grassmann nor classical. Instead, it's a sum of a Grassmann number and a classical number. So we could remove that postulate if you like. Okay. Good. Okay, you're right. So all of the calculations that we're going to do as far as the derivation of the path integral generally don't require one to add together classical numbers and Grassmann numbers. But I see that in order to make some of the calculations simpler on the problem set, the ones that I wanted to do, I actually did end up adding together Grassmann numbers and classical numbers. So sorry about that. Okay, so let's remove that postulate. Sorry about that. Thanks for pointing that out. Good. Good. Any other questions? Excellent question. Good. I mean, usually, I'll just say as a parenthetical, usually the situations where one actually finds it useful to do things like add together classical numbers and Grassmann numbers is somewhat more fancy situations like computations involving fermionic symmetries and things like that, which we're really not going to focus on in this class. Okay. So I added that postulate just to make life simpler, but then I see that on the problem set, in order to make the problems more computationally easy for you, I actually did do things like set some coefficients equal to 1 that I should have probably set to be a Grassmann number. Good. Okay, thanks for pointing that out. Excellent. Other questions? Yes?
Is there any way to put these into sort of more geometric objects?
Absolutely. I mean,
It sounds a little bit like the geometric algebra.
well, if you know what a differential form is, then differential forms are, are just another word for Grassmann numbers, essentially. So if you've seen what a differential form is, a differential form, right, is typically denoted something like dx or dy. So for example, when you write down an expression like the integral of some planar volume, integral dx dy, then the symbols dx and dy are things that you define formally in your classes on calculus. But one of the things that they don't teach you is that dx and dy actually have independent geometric meaning, sort of as objects known as differential forms. And in particular, they're objects that have a multiplication rule where they're multiplied together using something called the wedge product. So, and it has the property, this wedge product has the property that dx wedge dy is dy wedge dx. And in fact, this is something, minus, good. There's a reason I left a little space there, good. And in fact, this is something that you all have seen in a great deal of detail in your classes on multivariable calculus and linear algebra, except you called it the cross product, not the wedge product. Okay. So for example, if you take two vectors, v and w, then their cross product is minus w cross v. Okay. So this Grassmann product that we're talking about, you could think of as a sort of simple, it's not a generalization of the cross product of vectors, it's a simplification of the cross product of vectors. Because the cross product of vectors is something that I never remember how to compute. You have to put these guys in a matrix and take a determinant or something like that. Never quite remember. But I'm sort of joking there, but you have to put an epsilon symbol. But the Grassmann product of two Grassmann numbers is just this thing that anti-commutes, and that's what it does for a living, and that's it. And it's all quite simple. Good questions. So yes, so you can think about the algebra of vectors, the multiplication of vectors under the cross product as a sort of example of an anti-commuting product. Good. Any other questions? Excellent. So, in order to study the path integral quantization of fermion fields, we need to do things like perform a path integral over all possible fermion fields. So we need to integrate over the classical Grassmann variable d psi. So that means that we need to define what we mean by the integral with respect to a Grassmann variable. And now, what I'm going to do is I'm just going to give you a particular definition of what I mean by the Grassmann integral. But in order to motivate this definition, let me just talk about what sort of properties it is that integrals obey, which we want to preserve when we define the Grassmann integral. So in particular, what I really want to do is I don't care about doing a definite integral where I integrate from, say, some initial to final value of the Grassmann variable theta. Instead, I want to write down the analog of the complete integral from minus infinity to infinity of some classical variable, some commuting number x. That's really the sort of integral that we need to do when we do some sort of quantization. We need to integrate over all possible positions of a particle, for example, or all possible values of the field. So we really don't care about trying to define what we mean by a definite integral. Or rather, an integral from any variable. We don't need to define what we mean by the indefinite integral, where you vary the endpoints. We only care about the definite integral from minus infinity to infinity. And in order to define this integral, I'm going to require two things. The first thing that I'm going to do is I'm going to require that if you integrate some function, which again, all functions are linear, I'm going to demand that the integral is linear. So remember that the integral of the sum of two functions is equal, in regular calculus, is the sum of the integral of those two functions. Okay? So that means the integral of, say, f plus g is the integral of f plus the integral of g. So I'm going to demand that the same thing is true here. And the second thing that I'm going to demand is that the integral is invariant under shifts of the integration variable. That is to say, the integral of f of theta plus eta is equal to the integral of f of theta. And in order to motivate this, I'm just going to remind you that if we were doing a normal integral of some function of x, then we could always shift the integration variable by shifting x to x minus y, say. And then, because we're doing the definite integral from minus infinity to infinity, this is just equal to the integral dx of f of x plus y. So I'm going to demand that, so this is really, the statement that you can do a change of variables of your integral, just like you can do the change of variables for an integral in normal calculus. So what does this mean? So explicitly, what this means is that the integral d theta of f of, say, theta plus eta, if we just take this linear function here, that's the integral d theta of a plus b eta plus b theta. That, by our linearity requirement, is the integral d theta of a plus b eta plus the integral d theta of b theta. And that is supposed to be equal to the integral d theta of f of theta without the shift. So that should be equal to the integral d theta of a plus the integral d theta of b theta. So in particular, you could subtract off the integral d theta of b theta on both sides. And you would conclude that the integral d theta of something independent of theta has to be invariant under these shifts of a to a plus b eta. So what does this mean? The only way that this could be consistent is if the integral d theta of something independent of theta is equal to 0. And so the definition that we'll give to the integral, and this is really just a definition, I suppose, rather than something one can derive, is that the integral of an arbitrary function of theta should be equal to b. And this is consistent with the rule that we derived above. And this definition sometimes goes by the name of the Berezin integral. Any questions on this? And as we'll see in just a few minutes, so I promised you would know everything there was to know about calculus with Grassmann variables by 5, and I see I was 9 minutes early. Okay. So are there any questions before I continue on this? One of the cute things to notice that with Grassmann numbers, integration is the same as differentiation. right? Because the derivative of a plus b theta is b, so is the integral of a plus b theta. Now, this definition might seem to be a little weird, but as we'll see in a few minutes, this precisely reproduces all of this sort of, computations of the quantization of spinor fields that we've seen already in this class. And we'll be able to reproduce, for example, the computation of the spinor two-point function using path integrals with this definition of what we mean by an integral with respect to now the Grassmann field psi. In particular, to quantize a free fermion, in terms of path integral, we need to integrate over all of the psi's. But remember, the whole point of a free field is that the classical action is that of a bunch of harmonic oscillators. And the action of a harmonic oscillator is quadratic in X and P, okay? Or in the case of a field theory, it's quadratic in phi. And so, in order to compute the path integral for a harmonic oscillator, that basically boils down to a Gaussian integral. Okay, remember when we calculated the propagator of a free scalar field, when we calculated the generating function of a free scalar field, we ended up having to do an infinite number of Gaussian integrals. And so similarly, when we quantize the Dirac field, all we need to do is a bunch of Gaussian integrals. So what are the sorts of Gaussian integrals that we're going to need to do? So I remind you that when we quantize a complex field, we can view the real and imaginary parts of that field as independent variables, or we can view the field and its complex conjugate as independent variables. So that means that our spinor field psi is going to be expanded in really, you can regard psi and psi bar as independent variables. So we're going to end up doing path integrals of the sort where you integrate over the spinor field and the conjugate field psi bar independently. And roughly speaking, and I'll go through this in a little bit more detail in a second, this means that you're going to be integrating over two different Grassmann variables that we could call theta and theta bar. And you're going to end up integrating something Gaussian. And this is the integral that I was going to have you do on the problem set, but I decided it was a little too hard. You're going to end up having to do integrals of this sort. You're going to have to integrate things like e, the exponential of theta b theta, okay? Some sort of Gaussian integral. So what is that integral? Okay. Can anyone do that integral? You can take b here to be a C number as opposed to a Grassmann number. So the exponential is defined just as it is for a regular C number. So it's 1 plus the argument squared plus so on and so forth. Now the integral d theta of 1 is equal to 0 by definition. And so you're left with, so this is equal to the integral d theta bar of 1 plus theta bar b times theta plus that quantity squared plus that quantity cubed and so forth. But theta bar b theta times theta bar b theta is equal to 0, right? Because they're Grassmann numbers and they all square to 0. So it's just equal to that. And so you get the integral d theta of, so you have to do, so what do you get? Well, you just get b. Because you first do the theta integral and then you do the theta bar integral. Actually, if I want to do, yeah, good.
Sorry, you said that d was a C number?
Yes.
So, but b times theta would be a Grassmann number?
Mhm.
and a Grassmann number times a Grassmann number
Is a C
is
number.
a C number.
Mhm.
Yeah, and sorry, sorry to interrupt.
Yeah, yeah, yeah. Good. Now, if I want to be super, yeah, okay. Okay. Yes. Any? Yes.
Yeah, I'm actually sorry, that's the same thing. Because B is a C number, then you integrate a Grassmann number times C number, which we could quantify to 0, and got B is 0. See what I mean? Because
Maybe I'm not quite sure what you mean. Yeah.
The integral d theta of A was equal to 0 up above,
Mm-hmm.
right? But so when we're
So
integrating-
maybe I should say this a little bit differently. So view this as a function of theta bar. Then it's something independent of theta bar plus something linear in theta bar. You do the theta bar integral, and it picks off the thing that's linear in theta bar, which is b theta. And b theta is linear in theta. So you do that integral here, and you'll pick off the thing linear in theta, which is b. Okay. Yeah. So, yeah, question. There's a sign also, which I'm about to
It's not
discuss.
bad.
Yeah.
I remember where I was going with this. So if theta bar b theta is a C number,
Mm-hmm.
then when we take the Taylor expansion, why would the second or third or fourth order terms be 0?
Good. Because just because something's a C number doesn't mean it's non-zero, right? So what is the next term? It's theta bar b theta times theta bar b theta. So just you anti-commute that guy through here to pick up a minus sign, and then you can commute it through here, you get no sign, and so this is minus theta bar b squared theta squared, which is equal to 0. Oh, and there's a theta bar squared, actually. Good. Excellent. Yeah, there's a okay, ask a question.
Yeah, I'm not sure I understood how you derive the Berezin integral.
Well, I defined the Berezin integral. I didn't derive the Berezin integral, if you like. I mean, really, strictly speaking, I should really put in be careful about the sign here. Because if you see what I've done is I've done the theta bar integral first. And the way that I defined the integral here, there's an arbitrary sign that goes into the definition of the Berezin integral. But I defined it so that I picked out the thing linear in theta with a b before the theta. Okay. And so here, I should really commute that thing over to that other side before I do the theta bar integral. Yeah. And because b theta anti-commutes with theta bar, you'll get a plus sign there. Good. Excellent. Good. Any other questions? Okay. You know, so this is the sort of standard Gaussian integral that you might do when you do the quantization of a fermionic field. And you should really compare this to, for example, the kind of thing that you would do when you did a, say, Gaussian integral in normal calculus. Okay. So let's say you did this integral. Or if you wanted to make life simpler, if you don't want to do two integrals, if you just did a single integral, a single Gaussian integral, you get 1 over the square root of b here. So this is a sort of interesting, and it turns out to be a very important qualitative difference between Gaussian integrals of Grassmann numbers and Gaussian integrals of commuting numbers. You can actually generalize this, and this is something that I decided not to assign you on the problem set. So don't anybody accuse me of not being a kind and generous person. So if you wanted to do an integral over n Gaussian variables, so let's say I have n Gaussian variables theta 1 up to theta n, so I'll call them theta I, and another n Gaussian variables theta 1 bar up to theta n bar, then you can imagine doing a more general Gaussian integral where you have an e to the minus theta I bar bij theta j, where B is some matrix, then this, well, can anyone guess what that is? Yes, it's the determinant of B. And in order to see that, you can just remember the analogous expression for a Gaussian integral of classical numbers. So this is 1 over the square root of the determinant of B. And you can see that when you do the Bayesian integral, that B that you got here gets promoted to the determinant of the matrix B. Okay. One way to derive this would be to go to some basis, some change of basis of the thetas where this B is diagonal. Okay. Good. And more generally, there's a slightly more sophisticated Gaussian integral that we can do. So I should call that I, where we add a linear term here. So I'll call this term, so I'll add a general term which is linear in both theta and beta. So I'll call that, say, eta bar I, theta I, plus theta I bar, eta bar. Here, I guess I had my indices down here, so I'll raise the indices here. So this would be the most general term linear in the thetas and theta bars that you could introduce. And this integral, so, is the determinant of B. So how would you do this integral? Well, you would do this integral by completing the squares. Okay. Remember the way that you do a Gaussian integral when you add a term linear in x in the exponential is you complete the squares. You shift x to x plus y in such a way that that becomes a pure Gaussian. Okay. You use the fact that the integral measure is invariant under shifts of x to x plus y, and then you just get the term that you extract from completing the square, which is the exponential of, well, in this case, it would be eta bar I bij eta j. And this follows simply by completing the square and using the fact that your integration measure is invariant under shifts of the integration variable, which was really the fundamental property that we used when we defined this Bayesian integral. So hopefully you can see where this is going, because just as with the real scalar field, where we interpret the path integral over the real scalar field as an infinite number of Gaussians, if you can do the Gaussian integral for the, a bunch of Gaussian integrals for Grassmann numbers, you can use that to quantize the free Dirac spinor. So in particular, the Dirac spinor can now be quantized using a path integral setup and what we want to do is we want to define a generating function which will be a function of some sources that I'll call eta and eta bar, which is defined to be a path integral over all possible values of now a Grassmann valued spinor field. And just as in the free scalar field case, this is going to be weighted by the Dirac action, so an integral d4x psi bar times I d slash minus m psi And we need to introduce some source terms. So these would be the analog of the j's that we introduced to study the generating function for the real scalar field. And treating psi and psi bar as independent variables, I've introduced sources, eta bar and eta, which are sources for psi and psi bar, respectively. So here, eta and eta bar are sources. The classical action is a C number. So these sources, eta, will have to be taken to be Grassmann numbers so that I can add them to the classical action here. So these etas are sources which are Grassmann numbers, so that, for example, eta bar psi is equal to a classical number, the sort of thing that you can exponentiate and add to an action. And moreover, because eta psi and psi bar are spinors, eta and eta bar will have to be spinors as well. So secretly, there are 4 of each, and this eta bar psi, for example, is involves a sum over the 4 spinor indices. But as usual, we're going to try our hardest to suppress those spinor indices when we can get away with that. Okay, well, so hopefully you see the analogy between this integral and this integral. So in particular, just as we could explicitly compute the generating function of a free scalar field as a function of the sources j, we can now explicitly compute the path integral for a free Dirac spinor as a function of those fermionic sources eta and eta bar. So what's the answer that you get? Well, up to some determinant factor, which is independent of the sources. So it won't really matter to us, but we could just call it z of 0. We get this exponential term, and it's the exponential of the integral d4x, d4y, eta bar of x times something that I'll call s times eta of y, where s is the inverse of the Dirac operator. And we already computed the inverse of the Dirac operator when we quantized the free Dirac field. What is it? Well, it's defined, it's also known as the propagator for the free Dirac field. Remember, the propagator is the inverse of the wave operator. So it could be written easily in momentum space. So as an integral d4p of e to the I px minus y of I times p slash plus m over p squared minus m squared. Or we could rewrite this term here more simply as I over p slash minus m. So here this s is the inverse of the Dirac operator, I d slash minus m. Okay. Inverse in the sense of a Green's function. So hopefully you all remember our derivation of the 2-point function of the free Dirac spinor, where we concluded that the 2-point function of the free Dirac spinor was precisely this propagator that I've written here. The propagator of a Dirac field, it's the fermion, or the spinor analog of the Feynman 2-point function of a real scalar field. Any questions on this? Yes.
When you talk about the propagator for free Dirac field, is there any difference when you add interactions?
There's no difference. No, the propagator is, so yes. So I should.
The propagator for an interacting field is the same.
Well, when I'm a little, yeah, the propagator that we use in the Feynman diagrams is the same. When we talk, the reason why I sometimes refer separately to the propagator of a free field as opposed to the propagator of an interacting field is that interactions can lead to corrections to the propagator. Okay? I mean, so this is not so I use that language because when we talk about renormalization, we actually will talk about how higher order terms can be incorporated into corrections to the propagator. Okay? So for example, and this is an aside, when we compute the full propagator of, so what is the propagator? So a propagator is something that you would insert into a Feynman diagram to connect two vertices. And a full propagator would include a sum over all diagrams of things with two endpoints. So you could write it like this, plus, say, if we're in phi cubed theory, something, or phi 4 theory, something like that. Well, I guess in phi 4 theory, the next correction would be that, and then that, and so on and so forth. So so when we study renormalization, we'll talk about the corrections to the propagator that one gets when one includes loop effects. But from the point of view of the Feynman diagrams that we're studying now, when I say propagator, I mean free propagator. Although, of course, so for example, of course, these effects are incredibly important, and we'll study them within the next week or two. Yeah. Good. Other questions? Okay. So that's what the generating function is. And the point is that just as with the bosonic scalar field, to get the correlation functions, what we need to do is take variational derivatives with respect to these sources that we called eta. So in particular, if you think about this source term, so now eta x is a Grassmann spinor. That's a function of a location in space-time. And we have the source term that we had in the action. So what was the source term? So it was eta bar psi plus psi bar eta. And the only important point that I want to make is that you might think that this is equal to psi of x. That's what it would be in a bosonic theory. But because you have to take this derivative and commute it through this psi bar here, or I should say anti-commute it through this psi bar here, you actually get a minus sign. Whereas, for example, if you wanted to pull down a factor of eta by taking an eta bar, a factor of psi by taking an eta bar variational derivative, you would not get that minus sign. So this would just be a psi of x.
Would the first one be a negative psi bar?
Psi bar, sorry. Good. Yeah, so there are some signs that one has to keep track of. And indeed, the entire point of all of these Grassmann variables is that it gives you a very efficient way of keeping track of all the signs that appear when you quantize fermions. There's no, if you wanted to, you could do this entire derivation without ever introducing a Grassmann variable, but you would then end up with a sort of complicated discussion about where signs go in all of your various formulas. So all these Grassmann variables is a convenient way of keeping track of the signs that arise when you compute things involving fermions. So for example, if you wanted to compute, say, the time-ordered product, the time-ordered expectation value of two spinors, well, okay, this guy is 0, right, because I need to put a psi bar somewhere. So let's put a psi bar there. So what is this? This is 1 over z times a variational derivative with respect to eta bar to pull down that factor of psi and a variational derivative with respect to eta to pull down that psi bar at y of this generating function, all evaluated at eta and eta bar equals to 0. And the only subtlety is that I need to put a minus sign in here in order to keep track of the fact that in the source term I had here, I needed to commute through one of these anti-commuting variables. Now, of course, the reason why I needed to write the expression, the reason why I needed to write this expression as a psi bar eta instead of eta psi bar is, remember that I have spinor indices everywhere. Okay. And eta is a 4-component spinor, and psi bar is a 4-component spinor. And the way that we can track those together is to get a scalar is you write psi bar eta rather than eta psi bar. Right? It's like, you take a 4-component column vector times a 4-component row vector, not the other way around. Is that how it goes? I never can tell. Okay, can't quite tell the difference between a column and a row, but I think you get the idea. Okay. And indeed, if you just look up at the expression that we wrote here for this generating function, well, we need to take a derivative with respect to eta and a derivative with respect to eta bar, and that pulls down precisely a factor of this propagator s of x minus y. Good. There's one comment that I want to make about this. Which is that you could ask what would happen. Well, so the first comment that I want to make is that I'm suppressing spinor indices everywhere. So really psi is a 4-component spinor, so you could put a spinor index there. Psi bar is a 4-component spinor, you could put a spinor index there. Really what I'm computing here is a 4x4 matrix. So you should really put a index there and a B index there. And then this S that I've written up above, this guy here, P slash, it's a contraction with gamma mu. Gamma mu is a 4x4 matrix. So this is really a 4x4 matrix here, which if we wanted to, we would probably write as SAB. You could then ask, well, what would happen if I wanted to try and compute a generating function where I put the psi and the psi bar in an opposite order? And you can see how, you would expect that because these are anti-commuting variables, you would get a relative minus sign. And indeed, you can see how that happens in this setup because eta and eta bar are anti-commuting variables. So if you interchange them, you would get a minus sign. So the general feature that you can hopefully see from here is that exchanging fermions in a correlation function will lead to a relative minus sign. Similarly, when we discuss the Feynman rules in momentum space for the discussion of scattering amplitudes, for each fermion in a scattering amplitude, you're going to get a minus sign if you want to exchanging two fermions. If you want to exchange two fermions. So, for example, let's imagine that you have some scattering process where you have two fermions, say, an electron and electron, that come to form some boson. I guess that boson would have to have charge 2 in order for this to be consistent with charge conservation. But let's just say that we have two identical fermions, two electrons, say with momentum P1 and P2 that come in to form a boson. Then if you consider a scattering process where you have fermions with opposite momentum, so we're exchanging the momenta of these two identical particles, then this will be related by a minus sign to that original diagram. Good. And there are going to be various other minus signs that appear when we try and start writing down Feynman rules involving spinors. Okay? And so there's going to be one more important Feynman rule, important minus sign, for Feynman rules involving fermions. Which is that for every loop in a Feynman diagram, that involves fermions, the Feynman diagram will pick up an extra minus sign. And this minus sign, it turns out, is sort of incredibly important. There's all kinds of interesting effects coming from loop effects in Feynman diagrams that are sort of qualitatively different from loop effects involving scalar fields as opposed to fermion fields. And this leads to all kinds of interesting physics. I mean, there are all kinds of places where you would naively expect to get positive answers and you instead get negative answers because you have fermions running in loops instead of bosons. For example, the discovery of asymptotic freedom, which is the statement that the strong nuclear force gets weaker at high energies as opposed to stronger at high energies, involves crucially the minus signs that appear in loop diagrams coming from this effect. Similarly, the theory of supersymmetry as a plausible theory for extensions to the standard model, the entire motivation for the theory of supersymmetry involves delicate cancellations between Feynman diagrams that arise precisely because of this minus sign. So in particular, the idea, roughly speaking, is that if you had some, let's say that we have some loop diagram here. So here I'm imagining a theory where I have a scalar coupled to a spinor. And you have some spinor that runs around in a loop. So say this is an electron, and you have some other field. It could be a scalar. This could be QED, and these could be photons, 4 external photons. Or this could be some other theory where you have a scalar coupled to a fermion. And the idea is that because you have some fermion running in a loop here, you're going to get an extra minus sign. And roughly speaking, the way to see this is that if you think about doing this diagram in position space as opposed to momentum space, then you have 4 propagators here that you're gluing together. Okay? So there's an insertion point. There's a location. Let's call them X, Y, Z, and W for each of those interaction vertices. And the contribution to the from this Feynman diagram is going to involve a product of 4 propagators. That is to say, a product of 4 two-point functions. So you'll get one propagator inserted at X, or let's say one propagator that goes from X to Y, another propagator that goes from Y to Z, another propagator that goes from Z to W, and another propagator that goes from W to X. And then the point is that you want to do the various Wick contractions where these guys get contracted together, just as we did for the quantization of scalar fields. And you can see that when you do that, you're going to need to end up taking one of these psi's and transporting it and anti-commuting it an odd number of times. Okay? So what you actually get is a minus sign from anti-commuting one of these psi's an odd number of times. Okay? I guess I don't want to dwell on this point in too much detail because by and large this semester we're not going to be studying very many loop diagrams, and this minus sign is the sort of thing that, you know, you just need to remember it as a rule. But I just want to emphasize that it's the sort of thing that you can derive quite clearly from the fermionic path integral, and it's incredibly important. I mean, I think it's suffice to say it's one of the most important minus signs in physics. Okay? I mean, I sort of gave you just a very sketchy derivation of it here. Maybe, yeah. Is the idea more or less clear? I mean, I don't want to dwell on it too much. But the idea being that whenever you have a bunch of fermions running in a loop, if you just track through carefully the derivation of the Feynman rules, you'll end up having to anti-commute something through an odd number of times for every loop. Okay? And so that's going to give you a relative minus sign. Yeah, it's important enough that I probably, well, it's not something that's sort of the thing that I might want to squeeze in at the very end of a lecture, but I guess that's what I did. So, any questions? Good. Okay, I will see you in next class.